Hello everyone. So we are back again, and what we are starting in our previous class is understanding the solution results that we obtained from the simulation using fluid model, and we are trying to understand why this zone is having very high pressure. Although you know that this is an open channel and there should not be as such any obstruction, but it is the electromagnetic body force which is posing as a virtual wall over here, and that is not allowing the fluid to flow from this region and making the pressure to extend so high here in this zone, and the pressure is falling only near the exit, and finally it will enter into the atmospheric pressure. So that is there, but this zone is having very high pressure. And how it is originating? So to understand that, first we understand that how the current density vector is distributed near the cathode zone. What you are seeing here, see, this is the cathode end, this is the hafnium insert, and this is the nozzle exit zone. I have used again a cutting torch configuration. So this is 1 millimeter, that nozzle exit. So diameter will be 2 millimeter. This is the radius, and just for understanding purpose, we have chosen this example how the this pressure is so high in this zone, and this is again showing you very clearly that the velocity is only picking up in this zone. In this zone, the velocity is very low. You see here, this is almost zero over here, and then the velocity vectors, this this axial velocity I have plotted, and that is just picking up near the exit zone. Otherwise, see, this zone is having nearly very small velocities, and here it is nearly zero. Now why it is? Because the pressure difference causes the velocity, and you have seen that this zone is having almost uniform pressure. So if two zones are having the same pressure, it doesn't actually allow the fluid to flow so from one region to another, because their pressures are same. So when there is a very drastic pressure difference, then that causes the velocity to increase very rapidly, and this is the zone where you are having that thing. Now what is the current density and why the pressure is rising over here and why the pressure is dropping over here? So it has origin to the distribution of current density vectors. So here you see that this is the nozzle region, and the current density, as I told you, as you go towards the bluish side, then you get more and more current density, and the maximum current density is seen over here near the cathode surface. And in the nozzle zone also, you see here, this is the bluish zone, so this is having quite high current density. And the thing to note, I told you that this is a diverging section. This vectors basically shows you the direction of the current density vectors, and here it is in this direction, here it is converging towards the cathode. So this is a diverging zone and this is a converging. So this much is clear to you. Now I come to the thing how in a plasma device this matters. You see, in this zone, this is a diverging zone, right? This is a diverging, the current density vectors are diverging. This is the cathode, this is the nozzle, and below that there are many segments which can be added, and where you can inject the gas. In one case I have shown you the simulation where we are injecting the gas from the side and how that was affecting. So I will explain all these things over here. Now you see that here in this zone, what is the thing? This is the Z is converging. Current density vectors are converging because they had to enter into a smaller zone. Here the diameter is more, here the diameter is small. The channel diameter, this is the nozzle exit diameter, and this is the other segments that is put in the downstream. So from a larger diameter, it is trying to enter in a smaller diameter. So naturally they are converging, the current density vectors. Then once it goes through the region, then it is expanding. You are seeing there, it is expands and then again converges to a particular point near the cathode surface. Okay, so in this zone A, what you are seeing, this A, then in this zone you see that C, and this again, this is the E. In this zone, in typical your plasma configuration, you will see that the current density vectors are converging. So you see this, follow this blue lines, these vectors So this is the current density vectors and they are converging. Whereas in the zone like B and D, you find out where B. So this is a diverging zone, diverging current density. And then again D, here also it is a diverging current density zone. Now, this kind of configuration can be obtained by pushing gas from the sides so that you are cooling this zone. Once you cool, what happens? There is no plasma, because once it is cooled down, then it is just a neutral atoms, so they cannot carry current. So that is why it is shrinking, because you are pushing the gas from the surrounding region. So that is cooling the plasma there, and then they are constricting the current density vectors over there. So that is why this particular kind of configurations are coming. So this can be done once like this, then you know that in this zone there is no such gas injection. Still, because of the cathode and the nozzle configuration, they are expanding and then again they are converging. So this kind of converging and diverging current configurations are very common in plasma devices, and they are the agencies who is creating the pressure through electromagnetic body force. Now I will explain how they are. So you are now clear that there are certain zones where the current density vectors are converging, and there are certain regions where the current density vectors are diverging, like this zone B and D here, and this is the these are the zones A, C and E. Now you see one thing in this zone. Let us see that where the current density vectors are converging. Now you apply your right hand rule and you see that because of this current density vectors, you are getting a current like this, magnetic field like this. This is a B, okay, because each current is producing a magnetic field like this. So if you can use the right hand rule, and you will be able to see that this is the correct direction of the magnetic field. Now you apply your J cross B force law, J cross B. So J cross B is pointing in which direction? This is the direction. Normal to this J, normal to B. Basically, you are drawing a perpendicular to the surface of the cone that it has constructed. So this is the vector. Now you can split it into two components. So one is your horizontal component and another is your vertical component. So this vertical component is downward. You can see that the horizontal component from all through this perimeter, they will cancel each other, because for each vector like this there will be another vector like this which are radially just opposite, they will cancel, and for every point you will find another point which are there to compensate each other. So this radial pressure, there will be force will be balanced by each other, and there will be net force downward. This is the net downward thrust. So because of that, the plasma in this kind of configuration will be pushed down. So that will form a jet that we call usually cathode jet when it is originating from the cathode. Okay. So this plasma jet is now putting a thrust downward. Now the other way, when the current density is diverging. So I have explained it over here. The current density is like this. Now you see that here in similar way, if you analyze, then you see that they are producing a magnetic field like this, and the force J cross B is in this direction. It will have a horizontal component like this which are acting radially, and similar way like previous case, for each point like this there will be another point just which are cancelling each other, this horizontal force component, and there will be net vertical force component here which will be clubbing together and put a net upward thrust. So these zones where there is a diverging diverging kind of current density configuration like B and D, you will find that the plasma is putting upward thrust. So this one, although physically there is no barrier over here, you can see this is a open channel, but because of the current density vectors, you are getting a J cross B thrust. Radial components are getting cancelled, but there is a net vertical thrust over here. So although there is no physical barrier, because of electromagnetic force there is a barrier, and that is putting an upward thrust. So because of that upward thrust, you are getting a very high pressure zone over here, and this current density vector again that is putting a downward thrust. So what is happening? Effectively you are getting a very high pressure zone over here. So earlier I promised that I will explain how the high pressure zone is existing in this region. So now I am able to explain that because of the upward thrust in this zone, because of the J cross B effect, and because of the downward thrust from here, because of the current density configuration, J cross B thrust downward, and in this region you are getting a J cross B thrust upward. So both combined, they are producing a very high pressure zone over here, which is helping our torch to operate in a much better way, and that is also making this region almost, flow free kind of zone, stagnant zone. The gas is not moving over here, and that is helpful because it is allowing your molten film of hafnium over the cathode to stay at its own place. Okay, so that is how our simulation is helping us to understand how the plasma device will behave and what are the physics that will be occurring inside just from the simulation. And we would not be able to guess about what is happening unless and until we knew that this is particular distribution of the current density vectors. Here it is diverging and here it is converging. So this diverging and converging configuration is giving us all those results. And again, you know that this current density vectors are distributed here like this. So the whatever the heating is happening in this zone only, and that is why you are seeing that the tube inside tube kind of flow you are seeing in a plasma device, because they are forming a virtual wall over here because of the current carrying nature of this zone, and this is a non current carrying zone. So there you will get no force due to this electromagnetic effects. Okay, so that is why this is the this particular kind of distribution in velocity you are observing. So you now know that even though you keep a bigger nozzle, you will be able to put maximum velocity, you will be able to confine the maximum velocity in this zone. This is nearly half the zone, you see 0.5 mm. So even though you have a open space quite larger, but you are able to confine the jet because of the electromagnetic body forces. You are shaping the plasma jet in a way that the velocity is confined only in the half the diameter of that channel. So that is why you will get a very fine cut in such devices. Now I will just for better apprehension of the results, I will just show you simultaneously together how the temperature and the pressure varying together as the simulation proceeds, as you switch from some gas distribution to your equilibrium property effect on the plasma temperature and pressure, and then what changes happen simultaneously in both these two when you switch from equilibrium property to non-equilibrium properties. So I will just show you that over here. You see that this is the distribution that you are happening that you are seeing in the zone when the simulation procedure is proceeding like that. Now you see over here the same effect. See now I initially I guess was that all were uniform pressure. Now see the pressure is developing over here. So this zone is actually atmospheric pressure, and you will see gradually that this 1.2 kind of region, you know that 10 to the 5 Newton per meter square, that will be coming over here, that will be the atmospheric pressure after a certain time. And now you see that the simulation is proceeding over here, and it is in the midway now, and it is quite behind, but still you see that it has reached a steady state, and this also is showing you, you see that the pressure is also reached nearly a steady state. So it is still developing, and you will see finally that when it reaches here, you see there is a bluish zone now originated over here. So that is the atmospheric pressure. So this plasma jet now discharging to atmosphere, and you are seeing that how the temperature field has been reached there, and how the pressure is attaining its value, which correspond to the equilibrium distribution. So equilibrium, rather I should say steady state distribution, because this is a non-equilibrium simulation. So you are getting a steady state distribution under non-equilibrium condition like this, and the steady state temperature distribution, this upper one is the electron temperature distribution, and the lower one is the heavy particle temperature distribution. So you are getting in this slide three distributions together. One is your temperature, electron temperature, heavy species temperature, and this one is pressure. So they are now, you see that here is equilibrium, and then non-equilibrium has come, and here also you will see sudden change, sudden change in area. Now the change has happened. So because of equilibrium to non-equilibrium property switching, you are seeing that the distribution is changed. It is a very highly visible effect in the temperature, but here it is not that high, but it is seen there. Okay. So that is how the simulation proceeds for different parameters inside the plasma jet. Now I come to the other very interesting thing. This device is enclosed, okay, and this wall is not, you cannot perforate it, because if you perforate, then the plasma or the gas will exit from there. So you need to keep it a solid wall kind of thing for operational purpose. Otherwise also you need to cool this, so there should be a cooling channel adjacent to it, which will leak if you just perforate it to see what is there, what is happening there. So unless you are able to access this zone, you will not be able to tell what is the temperature, what is the species distribution here, or what is the pressure or velocity. Is impossible to know. But simulation tells you the fact. This interesting plot is showing you the distribution of the fast ions, IN1. Now you know that maximum, what is that, 23, and then when you are coming to the yellow region, then that is quite less. Then this is a very nice distribution. It says that near the core in the center you will be getting lower distribution of the fast ionized state. Rather, if you go readily outward or if you come downstream, you will be seeing a denser distribution of this electrons or the fast ions, because this is happening because this is IN1 is the fast ion distribution actually. So this variation of electron density is proportional to fast ion density when it is singly ionized, but not when it is doubly ionized. But this is basically the distribution of the fast ions, IN1. Okay. So this region will follow the electron density distribution, but this region where it is less, there may be a bit more effect that I will explain. But interestingly enough, that this is giving you the distribution of the fast ions, and which is less at the core. Why it is less at the core? Because at the core in this zone, you have seen in the previous simulation results, the maximum temperature is there in this zone. So at this temperature, what is happening? You are getting second ionized state. So those who are the first ionized already in this zone, whenever they are coming in this zone, they are getting second ionized. So population of the first ionized states is getting converted into the second ionized state. That's why the population of the first ionized state, this IN1, is reducing over here. So it is not very less, but it has been dropped from this red to the yellow zone. Okay. So the density is becoming less because of the presence of the second ionized states, and the first ionized states is getting converted into second ionized state. That's how they are lowering their population. And here in this zone, the temperature is low, so there is no second ionized state as such. And what you are getting? You are getting a more or less uniform distribution of the first ionized state. And as you are going away, you are seeing that the ionization is falling down, and finally there is no ionization. So ionization is 0. So first ionized state is not there. So this region is having cold gas, and here you can see it is very clearly that this zone, you see that there is no ionized states. There is a layer which is completely blue, and the blue zones means that they are not ionized. So this is the cold boundary layer, and it is obvious that they will not be ionized, and this cold boundary layer basically is saving the electrodes that I have told number of times. Now if we go for the second ionized state, so this is O++ density, and this was basically O+ density. So electron density you just correct it as the fast ion density here, and you can understand it better. And then you see that where we have seen that the fast ion density is low in this zone. You remember? Now you see that this is the zone where you are seeing the maximum density of the second ionized state here. Okay. So now as you go away here, you have seen that there is no second your secondary state. So only the first ionized states are there, and you have seen that this region is quite uniform here. You see that this region is quite uniform, and then as you go away, there is no question of the this second ionized state, because they are anyway cooler region. Now here you are seeing that some significant distribution of this second ionized state is there. Now if you come to that, this is the zone, you see that the temperature here, or if you go to the previous one, you can see that how the temperature was evolving here, and this is the zone where you are getting the maximum temperature. So naturally it will result in the second ionized state. Some of them will be having the second ionization here, and here also you see that the density is reducing in this zone also. They are changing from red to yellow. Why it is yellow? Because some of them have been converted into the second ion state because of the very high temperature existing over there. So that is how what we are doing now. We are now able to understand what will be the species distribution. So electron density distribution, ion density distribution, or second ion density distribution, you are able to see over here. And why they are important? The thing is that some reactions which very difficult to say occur in with the molecules, the same reaction can occur much faster with the fast ionized state. Now the same reaction will be very faster if you are doing the same thing with the second ionized state. So that is how, so when some reaction doesn't happen in say ordinary gas, if you do the same reaction, try to do the same reaction in plasma state, that reaction happens copiously. So there are many applications where we are using plasma to get benefit of this effect. So we'll come to that when we are in the application side. Now here, just to understand whether the plasma that is coming out from such device is a thermal plasma or not. So thermal plasma means you have to have TE, electron temperature is same as the heavy species temperature. That is one of the requirement. Now here what we are seeing, that along the axis where you are expecting the maximum temperature, you see that from just from the cathode, here it is the cathode, yeah, there you see that the temperature is quite high, and as you are going downstream along the axis outward, so this is this axis has been plotted over there, and you can see that around 14 here, the cathode end exists over here, and the current starts from there, and as you go to the exit here, it is around say 22 or something, and here 21 maybe, and here you are seeing that this is the 21. So where the plasma jet is discharging into the your process zone, and you see that along the axis, okay, the T equal to TH is maintained, but as it enters through into the nozzle region, they are deviating a little bit, okay, and when they are discharging into the process zone, there is a significant difference between TE and TH. So this is the difference, okay. So but anyway, they are very close to each other, and they are perfectly matching with each other near the axis, near inside the device, but when they are coming into the process zone, they are varying, but the variation is not much. You see this much only, and it may be say 2000 degree Kelvin or so the difference. So they are more or less equal. You note that the axis that I have plotted, it starts with 22,000. Okay, so that is why if you took it 0, they would almost merge with each other. Just to show the difference vividly, I have chosen the axis in a much smaller zone, and there you are able to see that even with such expanded view, you are able to see that the equilibrium is maintained within the device in this zone. Okay, so you can fairly call such devices, that thermal plasma device where T equal to Th, most of the zone, but near the periphery, here you see the distribution is for electron temperature is quite high compared to this zone. So here the non-equilibrium actually exists, and that can play a very important role in arc connection, extinction and reconnection, because electron temperature is high, so they can promote connection to any zone over the anode, but there are many other things which influences that, which we'll learn later. So now when you want to extend the simulation in the process zone, so then this kind of things happen. You see here, here what we are seeing, that this is the process zone, this is coming out from the plasma, and initially, as you know, that we try with the equilibrium parameters, equilibrium properties, and then suddenly we switch to the non-equilibrium values. So you will see that it is proceeding, and I just put over here. You see that here the non-equilibrium properties we have given, and the oscillation started. The simulation is trying to converge but not getting converged. It is proceeding, and then you will see that after certain time, here it is the simulation now, and I just click it over here so that you can see it faster. Still it is oscillating, and I come over here, and it is now more or less converged, and when you come over here, you see that it is almost converged. The simulation is proceeding. You see that I have not stopped it, so it is moving, and you are not seeing any change in the distribution. So this is the the steady state non-equilibrium result. Okay, so that is how you proceed when you want to include the process zone as well. Now I told that in this class I will be discussing something about the design of the plasma torch, uh, how to calculate the efficiency of the device from the simulation, and would like to understand the jet characteristics as well. So here I have tried to tell you something on that. So this is the cathode, this is the conical cathode, and here it is, and this is the cavity in which you place it. This is the anode, and this is the nozzle exit. Okay, this through which the plasma jet comes out. Now what happens, when you operate the plasma device, the cathode is at negative potential and anode is usually grounded. But whenever you apply a potential difference between these two, the plasma jet will operate, because of initially you break down the gas using some high frequency, high voltage, and because of the bias, the current will start flow, and the flowing current will heat the flowing gas, and that will form the plasma. So this arc is established, and then the gas that is flowing all around, they are getting heated. And just for your information, this arc doesn't stay connected at this point. It can move here on the other side, because there is a surrounding channel. Anywhere on the inside of that channel, this arc can connect. So that way it can just move around and hit the gas, and the plasma may come out. So now regarding the device, we are always interested in the efficiency of the device, how it operates, and how to calculate the efficiency from the design itself. Okay, so I will explain you, because this is very much important when you are applying your simulation result to understand the efficiency of the device that you have developed just directly from the simulation. So I will just explain you all this in the next class. Okay, thank you.